you. So I want to start by thanking the organizers for this invitation. So I defended my PhD last November at Loyola University. And the beginning of my talk will be about the first results of my PhD. Then I will give many applications, and one of them is work in progress. So let me start by giving the context of my talk. So it will be I will use all the time dg-manifolds, especially splitted and graded manifolds. So this is the definition. This is n-graded manifold together with a co-homological vector field. Okay, so I think we are familiar with this definition. So I will also use this correspondence between n-graded dg-manifolds and Lie-Rinehart algebras. We're going to find this in the works of Voronov, Bona, Volonta, and Poisson, but there are other outside everyone. So,
sorry, I mean, if it's homological, wouldn't it be degree minus 1?
where?
I mean, wouldn't it be a homological vector field if that's a degree plus 1? That's just okay, I guess I just...
Okay. Okay, and then what I will do is, all of these things, I will do them in a purely algebraic way by replacing the manifold, smooth functions on M by arbitrary unit or commutative algebra. Also, vector bundles, sections on vector bundles, I replace them by arbitrary projective modules over O. Okay? Okay, but even by doing this, you can still do this theory in terms of purely algebraic way. Okay, can do this. Okay, let's start with this observation. So given our Lie-Rinehart algebras, so it comes with a sequence of vector bundles like that. So the sequence is complex. The first bracket, because of high Jacobi identity, in particular, it gives you it's equal to 0. This is a complex of vector bundles. And the last map, I noted differently because it's very special. I call it the anchor map. Okay, it is compatible with the last, with L1. So, since it is a Lie-Rinehart algebra, the theory bracket doesn't satisfy Jacobi identity. Okay, so but if we quotient by the image of E-1, so it goes to quotient to a Lie bracket. Okay, there's no problem for that. And in the income up as well goes to quotient because it is compatible with L1. Okay, this is a Lie algebra, and we got the income up, but this is not a Lie algebra. Why? Because this quotient has no reason to be a projective module, or so it can be. Okay, it's not necessarily the section of some vector bundle. Okay, this is what we call Lie-Rinehart algebra. So, Lie-Rinehart algebra are the same as Lie algebra, in the sense that it is only the algebraization of that notion. So, this is the axioms. This is this is the same axioms as Lie algebra, except that A is not a projective module. It can be arbitrary modules, okay, infinitely generated with no basis. Okay, it can be anything. Okay, we have the same axioms as we got an income map, we got a Lie bracket, we got Leibniz identity. Okay, everything. Okay. Of course, Lie-Rinehart algebras are very nice. Okay, but there is a problem. They are not projective. Okay, I told you that. And so we cannot talk about connections. Okay, as we used to. So to do differential geometry, okay, it's very bad. Okay, but in my PhD, so I managed to desingularize Lie-Rinehart algebra, in the sense that to find something, okay, that where we can do all the things. We got projective modules, we got connections, and yeah, you can do everything you want. This is one of the first results. is giving an arbitrary linear algebra A over a unital commutative algebra. As a module over O, it always admits a resolution. Okay? In the category of modules, there's always a positive resolution, even a free one. So what does that mean? Even A is doesn't have basis or is not a free module, but there's a way to resolve it in the sense that there is a sequence of free modules, E-1, I call them E-1, E-2, and so on, together with a sequence of maps. It defines a complex. This complex is acyclic. There's no cohomology. Okay, we call this full resolution of this module. This always exists without any assumptions. So, given such resolution, I prove that there is always a infinity algebra whose first bracket is the differential map of this resolution. And this infinity algebra is unique up to a topic. And we call it the universal linear algebra of A because it enjoys the universal property in some category. So exactly in the category context. Okay, by doing this, what we have done, so we lose a lot of things because before we had only a linear algebra without a lot of structure. We got only one Lie bracket and comma up and Jacobi. And now we lose this because we got many more structures. We got many spaces, a lot of brackets, but we gain something. What we gain is now we are using projective modules, free modules, so we can define things on generators. That's very nice. Okay, so in 2 words, what the theorem says is acyclic infinite algebras are the same as linear algebras. That means give me a linear algebra, I will give you an acyclic infinite algebra, which is canonically associated to the linear algebra. And this result generalizes a previous result that was in the PhD of Lavo, followed by a paper with Camille, Jambou, Lavo, and Shadow. And it wasn't only for solvable singular relations. It's very special class of singular relations. Singular relations is a sublinear algebra of the algebra of vector fields on a manifold which are finitely generated locally. Okay, solvable here means that there, as a module inside vector field on M, okay, we need that it has a projective resolution in the category of vector bundles. Okay, so if this happens, we say it is solvable. So my result is valid even for non-solvable singular relations. With no assumptions, we can do this. Okay, so I want to share this example with you. This is considering a sub-affine variety of Cn. Okay, assume this is a complete intersection. That means the ideal is generated by a regular sequence. Okay, the ideal of this affine variety. Taking the causal resolution, and we can construct very easily, very explicitly, a full resolution of vector field that vanish on this sub-affine variety. So I managed to construct the universal infinite algebra in a explicit way. So this is the infinite algebra of this linear algebra. Okay, we got the brackets and the income and so on. Okay, let's go to.
Could you go back? That was too fast.
So I didn't want to give too much details on
You did get the details. So just get are we allowed to have 1 second to read?
Yeah, yes. And there are many geometric applications. Of course, the first one I put singular relations because the first motivation was singular relations, which are sublinear algebras of vector field on M, which are locally finitely generated. And I also use it to desingularize singular solutions using a Nash-like method. So if I have time, I will explain this, okay? This is one of very interesting application. And also we can apply it to singular subalgebroids, which was studied by Zambon and Ludakis, which is a particular case of Lie-Rinehart algebra. Weak symmetry actions on singular solutions. This is one of the results of my PhD. I will talk about this very later. And also, there's many examples. For example, vector fields on alpha varieties, they form a Lie-Rinehart algebra, so we can attach our Lie-Rinehart algebra to them, and so on. And the last one, which is now in progress, is about integration of singular solutions to Lie-Rinehart groupoids made by finite dimensional manifolds. So I will explain this also. Okay, let me introduce the first application by this motivating example. So assume we have a alpha variety, W, okay, in Cn, CD, okay, I call it CD, okay. Let's say it's something like that, okay. So, and we have a Lie algebra G that acts on W. Okay, what does that mean? This means this is a Lie algebra morphism from G to vector fields on W, which is the derivation of functions on W, polynomial functions. Okay, it's natural to ask if this action can be extended to an action on the event space. Okay, if I call this rho, and whatever, and this will be vector fields which are tangent to W. You know, every vector field here can be extended to the event space. There's no problem. But can you extend in a way that it preserves the bracket? This is a very natural question. So, and the question, when you see it like that, there's no singular solution around, there's no Lie-Rinehart algebra, but we can formulate this in terms of those structures. So let's first formulate this question in terms of singular solution. If you take an arbitrary length, you can always do that, okay? So the failure of being a Lie algebra morphism is valued in vector fields that vanish on W. IW is vector functions that vanish on W. These are vector fields that vanish on W. It's okay because it's good because it's actually G acts on W, not on the whole space. So when you restrict to W, you got a strict Lie algebra morphism. But when you lift, you got a failure, which isn't there. Okay? And this is a singular solution. I mean, this is a Lie-Rinehart algebra, which is finitely generated. It's stable under the bracket and so on, okay? And there is another property, is if you take an element here, you take the image, you take any vector field in there, any element there, you take the Lie bracket, okay? This will lie again here. It will be another vector field that vanish on the way, okay? So in terms of singular solutions, what this tells you, it tells you that the image of this map is an infinitesimal symmetry of the singular solution. So that if we formulate this problem like this, so what we get is what I called weak symmetry action of a Lie algebra G on a singular solution. So
is it okay that the arrow goes in the opposite direction of the
where?
slide?
On there, you mean to have the arrow going up, up, down. That's what she's saying. On your drawing.
I'm sorry, this is, maybe I should do, no, this is W.
Because otherwise your lift is just composition, right? So.
No, this is the same thing about there. Why is it moving by this direction? This is the same thing.
No.
This map?
Yeah.
It's upside down. It's upside down. That's all. Yeah. On the board.
This is the same map. This is the same diagram. I put this there. If you flip this like this,
Yeah, CD to W. Here it's W to CD.
CD to the sorry. No, yeah, this is the projection. No, it's sorry. Okay, sorry.
That's all you're saying.
Right. Okay, sorry. Okay. Yeah, this is the projection. Yeah, sorry. Okay. Okay, so the axioms, okay, as I just explained to you, we got a Lie algebra G and a manifold M, and G acts on M, and we call it weak. It satisfies these two conditions. Okay, now we formulate the problem in terms of weak symmetry actions, in terms of singular relations. Now, we don't answer the question yet. Okay, what we're going to do now is, using the previous results that I presented to you, is that having a solvable singular relation, we know there is a definite algebra associated to it. A dg-manifold, which is also a dg-manifold. Let's denote it like this, where E is the ergodic manifold and Q is the cohomological vector field. Okay, once we have a dg-manifold, it comes with a dg array given by ergodic vector field on E, and the ergodic commutator bracket, and the differential map as the adjoint action. Okay? This is a dg array. Okay? So, if you have a weak symmetry action, okay, can we lift it to the dg manifold of the singular relation? Because we can replace the singular relation by this dg manifold. But what does this action induce on this dg manifold? Okay, this is a result that I also in my PhD. It says that every weak symmetry action G on a singular relation leads to a unique optimal entropy definity morphism from G to vector field, okay, on the dg manifold. So G, you can see that the G array with the zero differential map, and this morphism is a really definity morphism. This is not a dg array morphism. Okay, it's weak, it's very weak. Okay, this is what we call infinity action of G on the ergodic manifold, on the dg manifold. Okay, again, once we do this, we can now answer the question. So this infinity morphism gives its second Taylor coefficient give an assertion class, well-defined class, of extending this action. And we even have examples where this class is non-zero. That precisely means that we cannot extend. The answer is no. Okay, this is one of the application of this result. Let's now talk about an application that I'm now working on, which is in progress. It's about integrating this dg array we have, okay, that we associate to the singular relation F, to a global object. It is, you can consider this as the infinitesimal part. What is the global object of this? It will be an infinity groupoid. Okay? This infinity groupoid the construction of this infinity groupoid is different from the constructions of Gessler's or Henriquez or Severa's constructions. You get the advantage to stay in finite dimension every time. I mean, we have a simulation manifold by finite dimensional manifolds. And the main tool that I use to construct this infinity groupoid is the notion of bisubmersions. So, bisubmersions. Yeah. So this is a notion that came from non-commutative geometry. It was invented by Onidakis Skandalis. So they use it to construct the holonomic groupoid of any singular relation. So this is the key point to construct it. So in my PhD, I managed to give a higher version of this notion that will help me to construct the integration of this thing to a infinity groupoid of the single folation. So before I introduce this, let me present you the definition. What is a bus summation? So a bus summation between two singular folations on M and on M, Fm and Fn, is another manifold, W, together with two submersions, okay, that satisfies the following properties. You got these two properties. So the first one tells you that, okay, if you pull back these two singular folations, you get the same thing. And the second one tells you it should be the sum of the kernels. So if you cross out the second condition, what you get is the notion of Hausdorff-Morita equivalence for singular folations that was studied by Gamonza and Zambon. So we do need the second condition because in the process of integrating the Lie-Rinehart algebra of the singular folation, this point is very, very crucial. So we do need the second condition. Okay, so theorem is bus summations exist. If you have a singular folation with no assumption, you always have a bus summation. And there's a way to take fiber product of bus summation, it gives you another bus summation for the singular folation. And there's a notion of inverse. You can invert a bus summation. So in some way, bus summation is like groupoid, okay, except that we don't have a product. So it satisfies what every groupoid satisfies. These two conditions, every groupoid satisfies. So in particular, every groupoid is a bus summation. And yeah, this is a groupoid-like object. Okay, now, before I give the definition, before I explain how I extend this notion to a higher version, so it's important to have a notion of equivalences between bus summation. So if I have a bus summation, W, between two singular folations, Fm, N, okay, let's say it's QR. Okay, I got number one here, I call it W prime, Q prime, R prime. Okay, so I would like to know, is there a way to identify these two? So to do that, we need something more. We need to have it will be interesting to have a singular folation W. Okay, what is the group candidate is the kernel of these two submersions, the intersection of the kernels of these two. Unfortunately, the intersection of this kernel in general is not a singular folation. So it may not be finitely generated, even though it is stable under the bracket. So in case it is locally finitely generated, you got a singular folation here, you got one here, and then we can talk about equivalences between them again. So the condition to have a singular folation here, given by the intersection of the kernels, if we start from a singular folation F should be solvable. So this is a result, okay? If F is solvable every time, this is a singular folation. Definition of the kernel. Okay, let me give the definition of what is equivalence. Assume that this is a singular folation again. So we call this singular folation bi-vertical singular folation. So an equivalence between these two is another equivalence between these two. That makes this diagram commute, of course. So this is like Morita equivalence for oligopoid. Okay, this is the definition of equivalence of bus summation. Okay, now I will not give formally the definition of the notion, the generalization of bus submersion. Okay, but let me explain the construction, the idea behind. Maybe I will, at the same time, give you how I managed to construct, how I will construct how the Lie-Rinehart groupoid is constructed. Okay, I'll start with a singular folation F. Okay? So I take a bar summation. Let's say, actually, let's call it W. 1. Okay, this is a bar summation. Okay, we got two summation. Okay? It's a bar summation. There is another, we can take a bar summation out of this. By taking the product, we know it's the final product of this is again a bar summation. Okay, so there is other bar summations. Okay, assume that, okay, let's take this one. W1, final product with W1 minus 1. Okay, let me put it here. This is again a bar summation. Okay? Okay, so we would like to know if these two are equivalent. Okay, to talk about equivalence, we would like to have a singular relation here, singular relation here. So this should be finitely generated. Okay. If F is solvable, yes. This intersection is a singular relation. The same here. So there exists W2 between these two, which defines an equivalence between these two by summation. Okay? Okay, we'd like to continue. We can continue the process, why not? Having this, we automatically have other bar summation. This is a bar summation with these two singular relations, the bivertical singular relations. But if we take the father of product in a good way, W2 3 times, it defines another bar summation between these two. Okay? And it happens that this, and under this condition that we always have the intersection of the kernels still define a singular relation, we can have an equivalence between them. Let's call it W3. Okay? So this way, we can go on and on, okay, under the condition that every step, the intersection is locally finitely generated. So we can go forever. And this is what I call tower of bar summations. Okay? So let me do it in this diagram. So I go from two bar summation. We got an equivalence between them called W2. Okay? Got another equivalence. And these two should be again equivalent. Got another equivalence. Every time this is bar summation. And we can continue. Okay? And this is what I call tower of bar summation. The bar summation tower. Okay? The slogan is a tower of bar summation is a sequence of equivalence between equivalences of bar summation. Okay? You take equivalence between equivalence and you continue. This is the same idea as taking resolution of modules. And example, of course, definitive groupoid or towers of bar summation. So just look at this diagram. So it's given by this diagram. Okay? You can check it's commutative every time, and everything works well. Okay, theorem is what I explained here. If there is a tower bar summation, if F is solvable, understand that F admits projective resolution in the category of vector bundles. And this is the theorem which is now in construction, in preparation. If you have a solvable singular relation, so it is integrable to a definitive groupoid and of finite dimensional. Okay? Okay, and the first truncation of this definitive groupoid gave the well-known holonomic groupoid of the singular relation introduced by Anudakis Kandaris. Okay, I don't know if I have some time. In addition, if F admits a positive resolution of length n, the positive dimension is n, so we got an n plus 1 groupoid. Okay, I can continue, yeah? Okay. I would like to end my talk with another application. I put it at last because I was afraid not to have too much time. And this is another nice application. It's about resolution of singular solution. So this method uses the same idea of Nash resolution for affine varieties. Let me explain very quickly. Nash says if you have an affine variety with a singularity somewhere, we can resolve it by doing some blow-ups, okay? But how he does this, he replaces every point, okay, the singular point is the problem, okay? We need to get rid of the singular point. So what he does, he replaces every point by its tangent space in the regular part. The tangent space every time. And by doing this, in the singular point, we replace it by we take the completion, okay, of this limit in the Grassmannian of this line, okay? And by doing this, we can resolve it to something like that, okay? Okay, this is the idea of Nash. It's taking the completion of the tangent space at the regular points in the Grassmannian, okay? So I can use the same idea. I use the same idea, okay, in terms of singular solution, the Lie-Rinehart algebra of a singular solution, okay, by taking the completion in the Grassmannian of the kernel of the income map, for example. Okay, by doing this, we have another set. Okay, in general, it is not automatically smooth, okay, but the singular solution on M pulled back to a singular solution in some sense, okay, on the blow-up. And the good news is we always have a projective singular solution at the end. It's like we got a singular solution F. This is a very bad module, okay? And when you blow it up, this thing is projective. Okay, noting that it is section of some vector at the bundle. And yeah, and you can continue this same idea by using higher level of this resolution of this complex, by taking the kernels, the completion of the kernels of the differential maps, and we got these results. And this result was this idea was done by Omar Musan for some special singular solution, I think linear singular solution. And yeah, and me, I generalize this and interpret this construction in terms of Lie-Rinehart inversely algebraic of singular solutions. Okay, so I want to thank you for your attention, and that's all. Thank you.